Ni hao Shanghai. It's the easiest way to get started. Who was here last year? Maybe some people remember my face? No? Oh, some people. Okay. Awesome. So last talk before lunch, there's still some energy in the crowd? Yeah? Nice. So, fine-tune and conquer. Yeah, I'm Matthias. I'm a senior cloud architect at DoIt, and today I'll be talking about Gemma, fine-tuning, and how these two came together for me in a customer support setting or customer servicing setting. So it's a bit of trials and tribulations. It was a bit of a random walk through trying to make the model perform better, and I hope to kind of share a little bit of the learnings I had, some of the pitfalls I fell into, and you guys can take away some of these and not fall in those pitfalls yourself. So without further ado, what we're going to look at is a bit of intro into Gemma. We're going to look at the use case. We'll look briefly at prompt optimization as well, because that was part of my journey, to finally end up with fine-tuning with Gemma. And then we'll look at some of the learnings and takeaways in the last part. So Gemma, the real MVP of today, not only Gemini. Maybe some people are wondering, did you misspell Gemini? No, I didn't. Gemini is definitely the flagship offering on running on Google Cloud's own infrastructure, but there's also a smaller version that is out in the open. And I've actually seen somebody wear a t-shirt with the Gemma logo, which made me quite happy. So these are the open models available for you to download and run on your own machine, on your own hardware. So what is an open model, you might be wondering? There's actually a few different flavors. So you have open in the sense of open weights, which gives you the weights for you to initialize your own model and query the model and play with it. But that doesn't fully allow you to maybe create such a model yourself. And that's where potentially things like open code come in. So that gives you the architecture of the model itself, the training and inference code. More than that, you need to also have the open data. So some models, some of the releases come with open data, and this allows you to look at what the developers of the model used to fully make that model what it is today. And some of the releases even include open training procedure, which might include the data cleaning, some of the hyperparameter tuning, the training logs, that gives you kind of the full suite to be able to reproduce a model yourself. There's not a lot of these. I think it's more of an academic thing. I think most of the models, open models nowadays, fall in the open weights category. Gemma is one. There is Llama. I think Llama is probably the most famous one because that's the one that first kind of got leaked. Europe has Mistral, the third one. Even OpenAI joined the open game now after a lot of model providers did that. And I think in this part of the world, probably DeepSeek, Quan, Kimi are the ones that are more well known. But even Middle East has Falcon. So yeah, kind of every geography is joining the open game. So why would we be interested? Because there's Gemini. Like, why do I care about Gemma, right? It's, Gemma has all the power. Yes, but think about your use case. So not all use cases would be applicable or would be fit for purpose for certain things. Like, imagine you want to generate a random color. You're going to do a lot of calculations just to generate blue, yellow, green, which might not be what you want to do. So if you have a certain case, the open models allow you to customize them to your certain use case. And with that customization, you can even get the same performance or a higher performance than you get with a large model. With that comes maybe increased efficiency, because the model is smaller, you're doing less calculations. Less calculations means probably lower costs. It means also probably lower latency. So there's a lot of nice side benefits you can get from looking also at these smaller models. And if you happen to care about it, all of these side effects also has a smaller environmental impact. One thing I particularly liked is that I could take a Gemma, download it, put it on my Mac, and start playing with the model locally. I could just talk to it, integrate it into my code, make sure the code runs before I start using a big model and spend my money on GPUs. And lastly, you might not be in the position to even choose if your customer says, don't send my data to these model providers. You're in the data privacy bucket and you just want to use those closed models. Yeah, Gemma history, I'll probably skip over that, but there's been 3 versions in the last 2 years. And the latest release includes 5 different sizes, so all the way from 270 million parameters to 27 billion. Both pre-trained and instruction-tuned variants were opened up, and then there's a few different use cases. Maybe you want to run at the edge, maybe you have a specific embedding use case. There's a lot of flavors which I recommend you to check out. Where to Gemma? Do you want to get started? There's a few options. Google AI Studio is probably the easiest way. You can just go there, create an API key, and start talking to the different sizes of Gemma. It's not available in the UI anymore. I think they took it off, but the second option is Vertex AI, kind of the Google Cloud offering where you can spin up your infrastructure, choose your model, put it there, and then start talking to it. Good for more production use cases and maybe fine-tuning. And it has some other benefits which we'll go deeper into later. And then Cloud Run, specifically for our use case, I was developing an application that was running on Cloud Run. Now you can attach GPUs to Cloud Run, albeit the small ones. I think it's NVIDIA L4s for now. I think they're coming with more models. If I remember correctly, the A100 is coming up. So Cloud Run is an option as well. So use case, a bit of context. That might you help understand what we were doing. So, as I said, I work for Doit. We try to deliver the true promise of the cloud by making it more accessible, and we do this through a few ways. One is FinOps platform, but we give our customers also on-demand access to 150 cloud architects all over the world. And it's actually about that part that I want to talk. How do we get access to those cloud architects? Let's see if the video runs. So basically we give our customers access to like any cloud provider at this point. Oh, I think we can put down the volume. Yeah, it's fine. So we let them type their problem, and we try to analyze as much metadata in the background as possible to avoid having them to fill out a whole form, as you might see in some cases if you want to talk to a company. It's getting harder these days, I don't know why. So for example, it tries to detect the platform. In this case, I was talking about Cloud SQL, which is obviously GCP. I detect the product, and we also nudge the customer to provide some technical details that might be relevant to the people that are serving the request. So, for example, what instance are you talking about? What query are you trying to run, etc. So this project is called CaseIQ, in which we try to nudge the customer to give us more details, and we try to take some work of them away by doing the form filling as much as possible for them. There's a blog post I wrote about some latency and cost optimization we did. If you're interested in that, I recommend checking that out as well. But the topic today, so we did some metadata extraction. What we wanted to do as a next step was extract the ticket type. So why would we be interested in that? Because ticket type, sometimes customers come to us to talk about my production is down. So that's kind of a break-fix scenario. Some customers just want to cost optimize. That might be a different person to talk to. I'm not a big cost optimization person. I'm more interested in running POCs and stuff like that. So that's the different ticket types, and it will affect the routing. So some of them will go to my colleagues, some of them will go to me, as well as it might affect the technical details we want to ask. In case of a break fix, we're not going to ask about how much money are you currently spending, because the person's production might be down, while on the other hand, if they're talking about a POC, we don't need to ask for the instance details of their broken instance. To get some baseline, another thing we did is create an evaluation application in Zendesk. So when somebody was serving the request, they got to see this on the right. And that basically gives us the ground truth data that my colleagues helped me label the classes. That gave me about 100 different ground truth labels, which we will see later was, problematic. So that gives us a problem. First step was trying to do some prompting, but naturally you end up wanting to prompt optimize, and that's where DSPY came in for me. So maybe some of the people in your companies have tried to do some prompting, and then the day after somebody comes to them and they say, the system is not working well for this particular case, can you maybe prompt in a different way? And they go about, and by fixing one thing, they might introduce 5 other problems. And that's what I kind of wanted to avoid. So DSPY is a framework developed by the people at Stanford. It stands for Declarative Self-Improving Python. And it basically does exactly this. It converts your prompt optimization from an undirected search to an optimization problem. How does it go about this? You have a whole workflow where you define your signatures, which is kind of a specification of your input-output and the task description. So kind of like, think of it as a prompt template. Then you have modules, which are the building blocks. It's kind of the built-in ways of how you're going to ask your LLM to solve the problem. Things like chain of thought, if you want to produce some reasoning, React, maybe in case of agents. So you pass your signature, your task, to that module to execute it. Then the dev set, which is what we got from EvalIQ, and then we give all of this to an optimizer to give us better results, right? So a signature looks a bit like this. You have the description of the task. In my case, I described the categories. I defined the ticket description, which was the input field, and then the output field was a ticket type with a set number of options. Same for the modules. In this case, we just passed the signature to the module predict a chain of thought. There's a bunch of them inbuilt. You can build your own as well if you want. So how do optimizers work? Optimizers basically will take your program and they will maybe rewrite some of the prompts. They might add some examples that they think are relevant, both from your training set as well as generated examples. And then they will optimize against the metric you define. In my case, it was we were optimizing for F1. There's a bunch of them. I tried 3. First one was Bootstrap Viewshot, which automatically selects those examples and then measures the results. Pretty straightforward. There's one called MyPro V2. That one basically looks at the characteristics of your data set as well as the program you wrote, and then tries to optimize the parameters both by rewriting the prompt as well as choosing some few-shot examples. This is done with a basic optimization. And then we have JEPA, which runs inference and then will look at the results. So it calculates the metrics, but you're also encouraged to write a textual feedback. So again, there will be a bigger model involved that looks at, okay, I classified this as a how-to. Can you explain why you did that? And if it's wrong, that invites the bigger model to rewrite the instruction again to do better the next time. Cool. There's a few papers about these two, if you're interested to dig deeper. But results, right? That's what we were interested in. The first try I did was just plain Gemma on AI Studio and Vertex AI. And the funny thing about AI Studio, or the nice thing that comes with Vertex AI at least, is that it comes with structured output. AI Studio does not do that, and that caused my results to be quite bad because half of the time it was just outputting explanations of why it chose a model instead of just giving us the label. And maybe something else you might notice in these results that is a bit off. Somebody wants to try? If you go down, the number goes down, which correlates inversely with the size of the model, which is, for me, it was unexpected. So we see that the bigger models are doing worse on the job. And that prompted me actually to look into what was going on with my data. As I said, we had 100 labels, which was not a lot. When I started looking at the different classes, I saw the whole data set was very imbalanced. Some of the classes had no examples at all. So yeah, it was kind of hard for the model to generalize. So first thing I did is try to generate synthetic data. So I took a few powerful models. I took some of the other cases we had, and I asked the models to output the labels for those cases. And the results were pretty encouraging. So there was a Cohen's kappa of 0.63, which measures model alignment, or alignment between the judges. And if I took only the rows where there was alignment between the three models, they were all outputting the same label, that went up to 0.72, which is substantial, moving closer to a perfect alignment between the model's judgment and the human labels, which it seemed reasonable enough to continue the journey. So what I did is I reran the experiments on Gemma 27B, and with the DSPY optimizers, the overall winning result was 27B with MyPro V2 optimization, which gave me a 0.9 F1 score, which pretty good. So on to fine-tuning, because that's what I was intending to do in the first place. Because 27B still requires, I think, 8 L4s, L4 GPUs. It's gonna cost some money. And I was kind of attracted by the notion that I could throw my labeled data set at a small model and then get maybe better results. So my curiosity was piqued. So who is familiar with fine-tuning? Who has tried fine-tuning? Few people, okay, nice. Mostly in the back, that's interesting. So fine-tuning basically takes your model, the weights that we talked about, and it will change those weights based on some new data you feed it. That would consist of a full fine-tuning process. But nowadays, usually when we talk about fine-tuning, we talk about parameter-efficient fine-tuning, which is a specific way of fine-tuning. You don't take the whole model, you freeze most of the model and only retrain part of the weights. Specific techniques, that is one that is very popular that you probably have heard of, is LoRa, in which we look at the weight update matrix, and we will decompose that one into lower ranked matrices to kind of approximate the big matrix, but learn a lot less parameters while we feed it the data set. So that's LoRa. There is a quantized version of that as well, so that's even a smaller model that you're gonna apply this technique to. The reason I mention that is because there's part of the release, the Gemma release, there's quantization aware trained models, which are models that were during training made aware of the quantization noise, and they try to kind of counteract that. I didn't test it myself, but I think it's something I want to try out, and I wanted to let you guys know, maybe if that's relevant. So LoRa, in images, we can see the weight update matrix on the left, but one gets decomposed into smaller weight matrices on the right. And yeah, there's kind of a whole set of techniques, parameter efficient techniques that are out there. With LoRa, we're in the reparameterization based techniques on the bottom right, but there are other techniques where we add weights to the model. Inside the model input-output parts, there's different techniques like the adapter techniques. But if you want to learn more about it, I think this was an interesting blog post on Hugging Face. So experiments. I ran my experiments in Colab Enterprise, which is part of Google Cloud, and it allows you to have a notebook environment that connects easily to some accelerator hardware. The experiments were written in Keras, so that's a deep learning API for fast experimentation. I got my models from Kaggle. So yeah, it has models, it has data sets, it has a community, which is nice if you want to see what other people are doing and learn from that. And then VerdixCI is where I was running my Colab, and in the end I was also deploying my models. But it has so much more. It has Model Garden if you want to try with other models as well. So the first try was not great. It was pretty much a fine-tuning fiasco, but I tried with 1 billion parameter model. I tried only one epoch, and basically I decided to apply more force, so increase the number of epochs. And what happened then is a whole collapse of the model. It started outputting only the most popular label, which was kind of a overfitting case. But I took a more structured approach after that, defining a few different sets of parameters to try with, like different LoRa ranks, different number of epochs, different learning rates, and at the end, through measurement, we got one model that had a 40% performance gain from F1 of 53 to 74, which it's not as good as the Gemma 27B, but for a 1B model, I was reasonably happy with that. The drawback was that it got better mostly at predicting the most popular class, which is going towards that overfitting. But for me, it was a reasonable outcome to change the technical details based upon of, maybe not to let it influence the routing at this point. Cool. So, on to conclusion. Yeah, what can we take away? One big takeaway for me was that the experimentation was not a linear process at all. It was very much a random walk. And I think by doing this exercise, next time I can do a lot better. Notebook, it looks a lot different from when you're doing that with an API. So a lot of the complexity is abstracted away. You don't have to deal with special tokens. You don't have to deal with schema enforcement, which I started looking into constraint decoding, and that was a very long rabbit hole and not a very productive one. So a lot of these things, they have engineered away for you, which is kind of nice. Discipline pays off. Clearly define your experiments, save the results, give it a proper name. I mean, this is probably the first thing you read when you start doing these things, but I still sinned against them the first time. Maybe, who's familiar with the guy on the right? Ollama? Yeah. So Ollama was for me also very helpful. It's kind of a way to run your models locally. I got a Gemma 1B running on my M2 Pro. I think a reasonable speed to do some initial experimentation. You're not going to run your whole data set through it, but to get the code running and get a sense of what comes back. Then check your data. That should have been the first thing I did. Instead of me going straight into prompt optimization, I should have checked what is in my data set. And I should have known there was a very imbalanced data set. I should have stratified my training set, my test sets. Yeah, it's a stupid mistake. But on the way there, I learned that synthetic data, which is something I was very apprehensive of when I started this. I was like, no, I don't want a larger model to come up with synthetic data. It's actually a reasonable option for you to explore. And yeah, I think Google did a very good job at training Gemma. Like 27B with some prompt optimization out of the box does very well. It got us to 0.9 F1 on my task. I think fine-tuning has still a place in your tool set, because you can improve your smaller model's performance by a reasonable amount, up to 74 in my case, and so do prompt optimizers. I haven't tried the combination of the two, but I think that's something I might try next. There's so much more to try. And yeah, in the end, it's all trade-offs, right? We can now deploy a 1B model that is going to be 5 times cheaper than the 27B, and we trade about 16 points of F1 for that. It might be a consideration for you, but in my case it wasn't, even because I'm running on Cloudrun and the only option there currently is 1B. And that's it. Any questions? I think we have some time. So I think the question was what the biggest difference was for me between a small model and a large model. So I think on easy tasks, the difference might not be super noticeable. I mean, it's not entirely correct what I say, because I'm still using larger models that will perform better at the task at hand than the small models out of the box. Yeah, I think it depends on your use case. If you need a big model to maybe think 5 steps ahead, take in a lot of information, I think large models are unmatched at this point. But if you have a very specific use case for which you don't need all that power, I think it's very sensible to start thinking about the smaller models. And at the end of the day, you want to think about the task. Can you measure it? And if you can measure it, you just test, right? You see, okay, this big model is performing this way, the smaller model can do equally good, or do I need to apply some techniques to squeeze out more performance? Does that make sense?
And I have a second question. Is it hard to deploy like the model to M chip or like the AMD chips, AMD graphic cards?
That I haven't tested. I mean, on my laptop, if you're talking Apple M chips or?
Yeah, M chip and like non-CUDA graphic cards.
So Ollama abstracts it away for M chips that I know. AMD, I don't know. I have not tested. I have not read any articles about it even. It's an interesting question.
Okay, and actually the question is it just like if you run on the Mac, is it just one script and then you can run it, one command, or like you need to adjust the configurations for it to run?
It's one, I think it's Ollama run and then the model name. And then it will pull the whole thing from their repository and it will start running it. I think, I'm not entirely sure, but I seem to remember it uses a VLLM to serve it to you locally. So you get the command line interface to talk to it in a chat way, but you also can point your API to it and then talk to it programmatically.
Okay, thank you very much.
There's someone there, I think. Oh.
My question is, for special functions, what is the highest accuracy that can be achieved through fine-tuning the model? What is the bottleneck? What is
Which is the bottleneck?
What is the bottleneck about to translate a big model to a small model that can be the same output, not changed a lot.
So you're asking about the bottleneck of why a small model cannot achieve the same performance of the large model on the same task?
Yes.
It's actually an interesting question because I didn't try running the whole evaluation on one of the big models. In this case, I don't know after fine-tuning if the big model will still outperform the smaller model. That's something I would need to test. In general, the big model comes with, it has ingested more data probably, or at least it has more parameters to retain certain subtle things that the smaller models don't retain because they have less weights to store it in. So they might not pick up on very subtle things that a bigger model can pick up on. That would be I don't think there's a scientific measure to do that, to measure inside the model. I think the only thing you can do is define your task, define your metric, and then query the model and see what comes out. If you want to answer for your specific use case.
So it is not include the effect about to the small model output. It is only to try more. 我不知道怎么说，就不是说在回答质量上，更加的，就是和大模型适应，而是说。
你说to be specific to be specific function. Sorry. What he want to say is to be specific function. How can the small model through fine tuning to get the better result?
Yeah, it is. I think the problem that all small models have is that if it is located on the like mobile, it cannot have a best output. 质量是什么来着?
I think you're right. I think you will always trade off some performance, but it will be impossible to run a whole TPU cluster on your mobile. So it's a trade-off of latency, capability, and where you want to run it. And what's the task at hand? Depends on what your mobile wants to do, right? If you're asking it a very deep research question, probably it makes sense to send off that question to Gemini, let it run inference in the cloud and get real results, only the tech stack on your mobile. While if you're doing the simple classification I was doing, maybe 1 billion model on your